Today we're going to be talking about finding the nth root of a complex number. Now, when you do that, we've got to first write our complex number. Of course, it came in the form, or usually does, a plus bi. We call that standard form. You have to find the modulus, distance from 0, 0, the origin, also known as the absolute value of this complex number, to find r, and then find the angle, which is usually the counterclockwise angle from the positive real axis in this case. Once you can write the complex number in trig form, then there's two things we can do with it. If you want to raise that to a power, you're going to use de Moivre's theorem, which says z, the complex number raised to the power n, is equal to the modulus raised to that same power, and look what happens to n. It becomes the coefficient of your angle. If we're going to find the nth root, this is a previous video, this is the new information. To find the nth root, well, I wrote them side by side to show you it's really nothing new. If you can do de Moivre's theorem, there's just a slight bit new. And the only thing new is that we're going to add 2 pi k to the angle. If you know de Moivre's theorem, then you can also find the nth root. Now the nth root, instead of n, I now have 1 over n. With the exponent on the modulus, I have 1 over n. The coefficient of our angle is now 1 over n. Now if I'm finding the 6th power, then n is 6. If I'm finding the 6th root, then the denominator of 1 over becomes 1 over 6, but n is still 6. So you've got your whole formula. It's simply de Moivre's theorem, but in parentheses on the angle, you have 2 pi k. Now what is k? K is going to be starting at 0 and your positive counting numbers, so your positive integers n 0, all the way out to n minus 1. Now, if we're finding the 6th root and you put in for k 0, 1, 2, 3, 4, and 5 and stop, that'll give you 6 roots, which also agrees with the fundamental theorem of algebra, which says if you're finding the 6th root, you should find 6 complex roots. If n is 10, then you'll do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that will give you your 10th roots. If it's 3, then you're going to put in 0, 1, and 2, and that will give you your 3 third roots. How do we find the roots of a complex number when the complex number is already in trig form? Well, here's a good example. Find the third roots of z equals negative 2 plus 2i. At least I say, whew, they only asked me for the third roots. So I know I'm hunt for 3 roots. That's the fundamental theorem of algebra. If I'm looking for third roots, I'm going to find 3 of them. Now, graphically, you'd find the x-intercepts as your real numbers. But if you're on a real number system, you're not going to see the imaginary solutions. So how do we find them? First, identify z as negative 2 plus 2i. And you must graph it. Graph it on this complex number plane with real in the horizontal axis and imaginary in the vertical. Negative 2 is your a, your b is 2, 2 root 2 if you know your trig. And that means your reference angle in quadrant 2 is pi over 4, so your second quadrant angle is 3 pi over 4. So this is the first step. You have to be able to write negative 2 plus 2i in trig form. R and theta are 2 root 2 and 3 pi over 4 respectively. So you've got z is equal to 2 root 2 cis 3 pi over 4. All right. Now we apply our formula. If our n is 3, then it's going to be z to the 1/3 and your r to the 1/3. And 1/3 becomes the coefficient of your angle. I tagged on plus 2 pi k. 1/3 becomes the coefficient of the angle. I tagged on plus 2 pi k. Unfortunately, this is one we need our calculator for. Put your calculator in radians, because we use radians, and report your answer to 4 decimal places. When I distribute this out, a reminder to go from trig form into standard form, we just have to distribute our r out. Substitute k equals 0. Well, actually, I could do this one without my calculator. If I put a 0 in for k, I could find that without a calculator. But these had a reference angle of pi over 12. So when you multiply out, you get these 3 solutions. Notice I wrote my solutions in a plus bi or standard form.